So infrared spectroscopy, after this UV visible, next energy level will be infrared spectroscopy. So it lays in between UV visible and microwave region. In between region is called IR. So this IR radiation, IR region, so IR region is in between this what UV visible and microwave region. This region is called the infrared region. So near infrared, middle infrared and far infrared regions will be there. So infrared range again what classified into three regions: near IR, which is very near to UV region; middle infrared region, 4000 to 200 centimeter inverse value will be there. Far infrared region is in the range of 4000 to 12,500 centimeter inverse. All these values are indicated in the form of wave number values. Near IR in the range of 10 to 200 centimeter inverse. 200 to 4000 is the middle IR. Middle IR is the useful region where we can find the functional group, where the fingerprint region is also present in this region. This middle IR is more informative, and most of the information is given by this middle IR region only. Now, let us go to infrared spectroscopy. When infrared light passed through the sample of any organic compound, frequencies are observed in that middle IR region that get transmitted. Whatever frequencies observed by the compound, so and the remaining amount can be emitted, that is called emergent beam of light. Then in infrared region, plots of transmittance versus wave number are recorded. Whatever spectra we are getting, that is recorded in terms of percentage of transmittance taken on y coordinate and wave number taken on the x coordinate, so that IR spectrum is obtained. Okay. When IR radiation of incident beam falls on the compound, which is a sample, so some amount of IR radiation absorbed by the compound and emergent beam of light is coming, that is emission of IR radiation is possible. Obviously, emergent beam of light intensity will be lesser compared to incident beam of radiation, because some amount of radiation is absorbed by this sample. This absorption mainly depends upon its concentration. Greater the concentration, so greater will be the decrease in the intensity of incident radiation. This is about the sample infrared spectrum of the compound. This spectrum is given for propane 1-ol. Here signals are appeared for this propane 1-ol. This region, this initial region which stands for fingerprint region, we can say this region as a fingerprint region. Above this 1400 to 4000, this region is called a functional group region. So whatever peaks obtained in this 1400 to 4000, so that corresponds to functional groups, and around 600 to 1400, this is called fingerprint region. The main distinction is due to here, whatever 600 to 1400 signals are mainly due to bending type of vibrations in the molecule, and 1400 to 4000, these are mainly due to stretching vibrations in the molecule. Stretching vibrations will give functional group identification, whereas bending vibrations are a specific type of information for individual compounds. So this is about this typical IR spectrum for propanol. Here OH functional group is there. When OH functional group is there, it is selective to give the peak in the region of 3300 centimeter inverse. Because of this peak, it indicates here we have OH group present in the compound. In this way, we can identify. So this is about the IR spectrum, sample IR spectrum of propane 1-ol. Now let us see what is the main principle involved in IR spectroscopy. IR spectroscopy is mainly due to vibrational and rotational changes, whereas UV spectroscopy we observe electronic transitions. In IR spectroscopy, the transitions possible are vibrational and rotational. These are less energetic compared to UV, because after UV IR radiation, IR region will be there. When Quantized amount of energy. Quantized energy is nothing but IR waves falls on the sample. It causes vibrational transitions. Single vibrational transition is accompanied by large number of rotational transitions. Nothing but when V0 nothing but ground state vibrational state. So that excited from V1 state, that is first vibrational state. When the species is exciting from V0 to V1, it is associated with large number of rotational transitions, because in the single vibrational level, large number of rotational levels are also present. Hence it is called vibrational rotational transition. IR is also called as vibrational rotational transition. Vibration is possible along with rotations. Along with rotations. In case of microwave region, only rotations are possible. In case of IR region, vibrations along with rotations are possible. In case of UV region, electronic transitions along with vibrations and rotations are possible. In this way, we can excite the molecule from lower energy level to higher energy level. No two elements except enantiomers have similar IR spectra. IR spectra is unique for each and every compound. That's why we can easily distinguish all kind of compounds which are present in this, which are absorbing light in this IR region. And now let us see what are molecular rotations, what are molecular vibrations. Rotational transitions are little used the spectroscopist. Rotations requires less amount of energy. So R0 to R1 very little amount of energy is required. That microwave energy is sufficient for that type of rotation. But molecular vibrations, in order to vibrate the molecule, IR region is sufficient one vibrational level to another vibrational level. So excitation is possible. Always that should be single step. That means V0 to V1 and V1 to V2 and V2 to V3. That type of excitation is possible, but not V0 to V3. The type of excitation it may not be possible in case of this IR spectroscopy. So IR spectroscopy is mainly IR spectroscopy is mainly used for vibrational and rotational type of transitions. Now, let us see the main principle involved in this IR spectroscopy. IR spectroscopy is associated with stretching and bending vibrations. Stretching is nothing but changing atomic distance, changing the bond length, nothing but interatomic distance along the bond axis is called a stretching vibration. Okay. Here bond distance will be varied. Bond distance by application of IR radiation, bond elongation and compression is possible. That interatomic distance will be varied. We can say bond length is varied by the stretching vibrations. Okay, so again these stretching vibrations are two types. One is symmetric stretching, second is asymmetric stretching. Symmetric stretching is nothing but if the bond length is changed in unidirectional, either outside or inside, only in one direction. If bond length is varied, that is called symmetric. In both the direction, if bond length is varied, that is called asymmetric stretching. One is uh, one is elongating outside, second is compressing inside. That kind of two different orientations are there, which is called asymmetric type of stretching. Now let us see how many types of bending vibrations are possible. What is bending actually? Bending in the sense change in the bond angle in between two bonds is called bending vibrations. Okay, when we are taking triatomic molecule, so if bond angle variation is possible, that is called bending vibration. Bond length variation is possible, that is called stretching vibration. Always stretching vibration requires large amount of energy compared to bending vibration. Here again bending vibration is four types. One is rocking, second is scissoring, third is wagging, fourth is twisting. Rocking is nothing but when two bonds are moving in only one direction, just like pendulum. In plane rocking in the sense, if two atoms are moving in one direction, that is called rocking. Just like pendulum, these bonds are moving. So one side rotation is possible. Scissoring is nothing but one of the bond is getting in, two bonds are coming inside and two atoms are going outside. So one is towards right hand side, second is towards left hand side. So just like scissors, how scissors is working, both are moving in opposite direction, coming inside, going outside at the same time. That is called scissoring. Scissoring type of bending is possible. Next is about wagging. Wagging in the sense out of the plane, inside of the plane, out of the plane, inside of the plane. So that is called wagging. How the dog tail is moving. So above the plane and below of the plane, the type of bending is possible. Both are represented by either plus sign or minus sign, but both are moving in the same direction. Twisting in the sense one of the bond is going up, second bond is going down, out of the plane, inside of the plane. So twisting, we are twisting both the bonds. That is called the twisting type of vibration. That twisting type of vibration is mainly possible. Twisting type of vibration is mainly possible when two bonds, one is moving inside, second is moving outside of the bond. So all these comes under bending vibrations, always bending, nothing but change in the bond angle. This include rocking, scissoring, wagging and twisting. Now, vibrational frequency. A molecule vibration occurs when atom or molecules are in periodic motion. They has constant translational and rotational motion. A frequency of periodic motion is known as vibrational frequency. Okay, so when the amount of energy which is required to vibrate the molecule, that amount of sufficient energy is called a vibrational frequency. That vibrational frequency ranges from 10 centimeter inverse to 12,500 centimeter inverse. 10 to 2000, 10 to 200 is called far IR. 200 to 400, 4,000 is called middle IR. Then 4,000 to 12,500 centimeter inverse is called what? Near IR. So in this way, infrared radiation mainly measured in wave number. So middle IR region only responsible for this functional group identification. This is about vibrational changes V0 to V1, V1 to V2, V2 to V3, V3 to V4. These are called the vibrational energy levels. So this type of transition is possible. When V0 to V1 transition is possible, this is associated with large number of rotational vibrations also. Okay. So overtones. In case of this IR spectrum, some new terms also there, overtones. Multiples of given frequency results from excitation of ground state to higher energy level. Overtone occurs when the vibrational mode is excited from V0 to V2, which is called first overtone. V0 to V3 is called second overtone. These are forbidden regions. Means these are not accepted by IR spectroscopy. If V0 energy level excited to V1, that is a fundamental. That means actually required one. When V0 excited into V2, that is called first overtone. V0 excited to third level is called second overtone. V0 excited to V4 level is called third overtone. Next V5 is called fourth overtone. Next is about vibration of the molecule in the IR region should causes changes in the dipole moment. This is called selection rule of IR frequency. When change in dipole moment is there, then only the molecule becomes IR active. This is called selection rule of IR spectroscopy. When HCl and CO molecules were taken, these are polar in nature. That's why these are called IR active. When hydrogen nitrogen molecules are there, these are called non-polar because these are IR inactive molecules. Okay, so absorption of vibrational radiation should cause transitions in the region, that is delta V is equal to plus or minus 1. IR region only one step excitation should be there. Just now we saw V0 to V1, that is only giving fundamental peak. When V0 to V2, that is first overtone, that is the forbidden region only, forbidden peak only. So these two are called selection rules for IR spectroscopy. One is change in the dipole moment, then only the molecule becomes IR active. Second is transition takes place from one level to next level only. That means only one step excitation is possible, which is given by delta V is equal to plus or minus 1. Now, number of fundamental vibrations in the given molecule. This is a very important term in the vibrational spectroscopy or IR spectroscopy. 3 and minus 6 degrees of freedom are present in the non-linear molecule. 3 and minus 5 formula is applied for linear molecule. 3 and minus 6 in the sense N stands for number of atoms present in the given molecule. If it is non-linear, the formula should be 3 and minus 6. When we apply this formula to benzene, benzene contains 12 atoms, 6 carbons and 6 hydrogens are there. When we apply the formula 3 into 12 minus 6, total 30 degrees of vibrations are present. Okay. For this benzene molecule, 30 degrees of freedoms are available. Therefore, number of vibrational degrees of freedom of benzene are 30. This is an important formula for the calculation of number of fundamental vibrations present in the given molecule. When we are taking carbon dioxide molecule, this carbon dioxide molecule contains 3 and minus 5 degrees of freedom because it is a linear. When we apply linear molecule, the formula will be 3 and minus 5. Number of atoms are 3. That's why 3 into 3. 3 into 3, that becomes
9.
9. And when we are taking 9, 9 minus 5, it will be 4. So in this way, 4 vibrational degrees of freedom are available for this carbon dioxide molecule. In this way, we can determine whether the molecule is linear or non-linear. This is another application of this IR spectroscopy. Okay, so it is also possible to determine whether the molecule is linear molecule or non-linear molecule. And these are the what types of bending vibrations are possible in the molecule, just we discussed. Okay, so this is about stretching. Outside stretching, inside stretching is possible, called symmetric stretching. And this is, one is outside, second is inside. This is called asymmetric stretching. Here in this third one, what we are seeing, two atoms are moving in one direction, hence it is called rocking. Two atoms are getting inside and going outside, this is called scissoring. And wagging, in the sense both are indicated with plus sign, this is called wagging, going up and going down. Twisting, in the sense one is going up, second is going down, this is called twisting. So stretching, bond length changes, bending, bond angle changes. This is the main principle of that one. And IR spectroscopy, what happens? Infrared light falls on the sample, liquid or solution, finally used to detect that molecule. Okay, so it is type of absorption spectroscopy. How much light absorbed by the molecule we are going to determine. Especially functional group identification is possible by using this IR spectroscopy. Always IR spectroscopy, absorbed light causes vibrational and rotational changes, and always there is a change in dipole moment is possible. Dipole moment when changes, then only the molecule becomes IR active. Two compounds will have similar IR spectra. This is a important condition. Each and every compound have their unique IR spectral lines based on their stretching and bending vibrations.